The next step in our study of the trig functions is to define the inverse sine, inverse cosine, and inverse tangent functions. Let's start by reviewing the graph of the sine function. Okay, you can see I've drawn it here. Its domain is all real numbers. Its range is from -1 to 1. And our goal is to find an inverse for this function. Okay, it'll help you a great deal to think of these x values as angles. And so your sine function takes an angle, an x value, and spits out or gives out a y value, a real number between -1 and 1 that is the sine of that angle. What we'd like to do is find an inverse function that takes one of these real values, real number values between -1 and 1 and gives us back a unique angle. But there's a big problem. Notice that if I pick, say, 1/2, there are a lot of angles whose sine is 1/2. It wouldn't be a unique angle. And the term for this is not a one-to-one function. A one-to-one function doesn't have an inverse, so we have to do a little work to find an inverse function. We're going to take just a one-to-one piece of our sine function and work with that. Okay, so it might help to remember the horizontal line test from algebra. Right? The horizontal line test, horizontal line crosses more than once. The graph's not one-to-one. So we're looking for a little piece of the graph where when we draw that horizontal line, it'll only cross one time, anywhere we draw it. There are a lot of those pieces. There's this piece, there's a piece here, and there's a piece back here, and so on. It's customary to take this piece. It starts when x is -π/2 and ends here when x is π/2. And this is the piece that we're going to work on. So let's draw this piece of this one-to-one piece of the sine function separately. We'll start here. This is -π/2, -1. Here's the point 0, 0, and then the point π/2, 1. And then we'll draw our sine curve. So this is our function, y equals sine of x for -π/2 less than or equal to x less than or equal to π/2. And we can see this is our one-to-one piece we want to use. Each of these angle or x values corresponds to one y or sine value. And furthermore, each y value corresponds to exactly one angle value. Since we have a one-to-one piece, we're ready to define our inverse sine function. So y equals the inverse sine of x is the inverse of our function y equals sine of x for -π/2 less than or equal to x less than or equal to π/2. This function, y equals the inverse sine of x, has domain with closed interval from -1 to 1. And range -π/2 to π/2. Okay, so our inverse sine function is going to take a real number in the closed interval -1 to 1 and return a unique angle in the closed interval -π/2 to π/2. Okay, one word about our notation. I know this looks like an exponent, this -1, but it's not an exponent. It's just a notational device. We read this y equals the inverse sine of x. It's not an exponent. The definition of the inverse sine function tells us that the inverse sine of x is an angle. We're going to call that angle theta. In the closed interval -π/2 to π/2, whose sine, S-I-N-E, is x. So we can write theta equals the inverse sine of x. It's just an angle. And we know that theta is in negative pi over 2 to pi over 2, this closed interval. So let's picture this here. Right? This is our usual coordinate system where we look at the different quadrants. An angle of 0 radians would be drawn here, pi over 2 radians along the positive y-axis, and so on. If angle theta is in the closed interval negative pi over 2 to pi over 2, then where could theta lie? Well, here's negative pi over 2. There's pi over 2, so it can be anywhere in quadrant 1 or quadrant 4. It could be along the positive x-axis, and it could be on either side of the y-axis, the positive or the negative. Okay? It would help us a lot to make a table that'll help us sort of track when x is a certain number, where does the terminal side of theta lie? Okay? So what are our choices? X can be negative 1. Remember, our inverse sine function has domain negative 1 to 1, that closed interval, so the smallest is negative 1. Okay. All right, well, where would that be? That would mean it was along the negative y-axis, the terminal side there. In that case, we actually know the angle right away. It's going to be negative pi over 2. Okay. All right. Anywhere in the fourth quadrant, the x is going to be, it must be a negative number, so we do from negative 1 to 0. Notice those are not allowing equal to, just an open interval. This is going to be in quadrant 4. If x is actually equal to 0, it also corresponds to theta equals 0. That's on the positive x-axis. X might be between 0 and 1. And that's going to make the angle have its terminal side lie somewhere in quadrant 1. And the last choice is x could be 1, in which case the terminal side lies here on the positive y-axis. And we know in that case that the angle would be positive pi over 2. I think you'll find this chart very helpful as you look at these next examples. Let's practice finding exact values using our inverse sine function. The first example is to find the inverse sine of positive 1/2. So remember, we're looking for an angle. We have to decide where that angle might be, and we know that its sine is positive 1/2. Okay. So in this problem, this is our x, and we can see it's positive 1/2, which is between 0 and 1. So we're looking for an angle in quadrant 1. Okay, in quadrant 1, the angles are positive and acute. And let's look at this x value more closely and see if it'll help us figure out which special angle is the answer. Okay. The sine of pi over 6 is 1/2, so there you go, that's your answer. The positive acute angle in quadrant 1, whose sine is 1/2, is pi over 6. Let's try a second one. This time, x is negative. It's between negative 1 and 0. Okay, so that means it's going to be, its terminal side is going to be somewhere in quadrant 4. Okay, it needs to be a negative angle in quadrant 4 because if you remember, the inverse sine function's range is negative pi over 2 to pi over 2, so we're looking for a negative angle. And I think we might want to use a reference angle to help us figure this out. Remember, a reference angle is a positive acute angle. We hope this is one of those special angles we know. the sine of pi over 4 is 1 over the square root of 2. So our reference angle is pi over 4. Okay, so let's just look at the angle and make sure that we pick the right one. We want a negative angle in quadrant 4. The reference angle is pi over 4, so this is actually that angle negative pi over 4. Okay, last one. Inverse sine of negative 1. Okay, negative 1 is one of these sort of special cases. The terminal side of theta will land on the negative y-axis, and theta has to be negative pi over 2. Let's turn our attention to defining the inverse cosine function. As we look at the graph of our cosine function, we see that again it is not a one-to-one function. So we need to find a one-to-one piece and define our inverse on that piece. Again, we have many choices, but the customary choice is to take this first piece from 0 to pi, and it's first from the origin, so that makes sense. Okay. We'll draw that one-to-one piece here and examine it more closely. We have the point 1, 0, or 0, 1, pi over 2, 0, and this one is pi negative 1. We're going to draw our cosine curve here. This is the function y equals cosine x, 0 less than or equal to x, less than or equal to pi. And we see that it is in fact a one-to-one function. We're ready to write the definition of the inverse cosine. Okay. So y equals the inverse cosine of x is the inverse of the function y equal cosine x on the interval from 0 to pi, closed interval. The inverse cosine function has domain negative 1 to 1, again a closed interval, and range the closed interval from 0 to pi. So this inverse cosine function will take in a real number from this interval and give us back an angle in the closed interval 0 to pi. Let's use our definition of the inverse cosine function to help us find exact values. The definition tells us that the inverse cosine of x is an angle, which we'll call theta, in the interval, closed interval from 0 to pi, whose cosine is x. Okay, so we're going to write this again a little bit differently. Theta is the angle theta is the inverse cosine of x, and we know that 0 is less than or equal to theta is less than or equal to pi. Okay, so where will we find the terminal side of such an angle theta? Well, it has to be from 0 to pi. 0 to pi, that's this part. Quadrant 1, quadrant 2. The positive x-axis, the positive y-axis, or the negative x-axis. Okay. Let's organize the information that we have. What are the possible values of x? Well, what's the domain of our inverse cosine function? It's the closed interval from negative 1 to 1. Okay, so if we have x equal to negative 1, then the terminal side will lie on the negative x-axis. And that is the angle theta equals pi. Okay. X can be something between negative 1 and 0. Okay, so that's a negative number that's going to lie, means the terminal side will lie in quadrant 2. X could be 0, in which case the terminal side lies on the positive y-axis. And so that means the angle theta is pi over 2. We have two more possibilities. If x is between 0 and 1, then the terminal side is somewhere in quadrant 1. Or x could be 1, and that means that the angle lies on the positive x-axis. And that would be theta equals 0. Let's look at some examples of finding exact values of inverse cosine function. Here's our first one. Find the inverse cosine of 1 over the square root of 2. Okay, so our x value is 1 over the square root of 2. This is between 0 and 1, so we know that we're looking for an angle in quadrant 1. In quadrant 1, our angles are acute positive angles, and we just need to try to figure out if this is one of our special angles that we know. That's right, cosine of pi over 4 is 1 over the square root of 2. So the angle in the first quadrant, whose cosine is 1 over the square root of 2, is pi over 4. Okay, the second one, the inverse cosine of negative 1/2. So in this case, the x value is negative 1/2. That's going to be in this interval, negative 1 to 0. That means the terminal side of our angle theta is in quadrant 2. Okay. Okay, so we need to figure out which angle that is in quadrant 2. We're going to use a reference angle to help us figure that out. The reference angle is the angle it's a positive acute angle whose cosine is 1/2. Right, the reference angle should be pi over 3. Let's draw a picture of the angle that is going to be our answer. It's in quadrant 2. The reference angle is pi over 3. And here's the angle we need. How do we figure this out? So it's pi minus our reference angle, or 2 pi over 3. Okay, one more. The inverse cosine of 0. Well, when x is 0, then we know that the terminal side of theta lies on the positive y-axis, and that makes our angle theta pi over 2. Let's now try to define an inverse tangent function. Okay, so the graph of the tangent function is shown on the board, and we see again that it is not a one-to-one function. So in order to find an inverse, we need to choose a one-to-one piece. Actually, each of the pieces is one-to-one. Any will do, but the customary choice is this piece that runs from negative pi over 2 to pi over 2. Notice that at the ends, those are vertical asymptotes. So we're going to choose the open interval from negative pi over 2 to pi over 2 to restrict the x's to. Okay, we'll highlight it here, and now let's draw it separately so we can look at it carefully. We have vertical asymptotes at pi over 2. And negative pi over 2. And then we just have this one piece. It is definitely a one-to-one piece of the tangent function. And we've restricted the domain to this open interval to get a one-to-one piece. We're ready to write the definition of the inverse tangent function. Okay. Y equals the inverse tangent of x is the inverse of y equals tangent x on the open interval negative pi over 2 to pi over 2. And this inverse tangent function has domain all real numbers and range the open interval from negative pi over 2 to pi over 2. Let's talk about using the inverse tangent function to find exact values. So from our definition, the inverse tangent of x is an angle, which we'll call theta, that is in the interval from negative pi over 2 to pi over 2, an open interval, whose tangent is x. And we can write this a different way. The angle theta is inverse tangent of x. So again, this is just an angle. And we know that negative pi over 2 is less than theta, which is also less than pi over 2. So let's look at where we find angles theta that meet this criteria. Okay, so negative pi over 2 to pi over 2 is here on the right side of this. It includes the first quadrant, the fourth quadrant. It includes the positive x-axis, and that's it. Because remember, this is an open interval, and the tangent is actually undefined at both pi over 2 and negative pi over 2. Okay, so we'll organize our information in a chart. If x is a negative number, then the terminal side of theta will lie in quadrant 4, here. If x is equal to 0, then the tangent of theta will lie on the positive x-axis. And that means that theta is 0. And the only other possibility is that x is a positive number, and that would place the terminal side of theta in quadrant 1. Let's look at some specific examples of finding exact values of the inverse tangent function. Okay, so our first one, inverse tangent of negative 1 over the square root of 3. So x here is a negative number. And whenever x is a negative number, the terminal side of the angle theta we're trying to find will be in quadrant 4. Okay. Right, that's the tangent there of one of our special angles, so let's see if we can find a reference angle. Okay, the tangent of pi over 6 is 1 over the square root of 3. So our reference angle is pi over 6. And we'll sketch a picture to make sure that we give the right name of our angle. So our angle theta is a negative angle in quadrant 4, and the reference angle is pi over 6. So here is the angle we need. That's right, it's negative pi over 6. Okay, the inverse tangent of 1. Okay, so we look at our chart to help us out. 1 is a positive number, so that tells me the terminal side of theta is going to land somewhere in quadrant 1. Okay, in quadrant 1, what's the special angle whose tangent is 1? Right, pi over 4. And we have one more. Inverse tangent of 0. Whenever x is 0, the terminal side of theta lies on the positive x-axis, so the angle is 0. Let's look at the instructions for this last group of examples. Use a calculator to approximate each of the following. Give your answer in radians. Round to 4 decimal places as needed. Okay, well, I've already worked these out with my calculator, but I'd like to talk to you about some helpful tips. The first thing is notice that you don't really have any other way to work this problem except for the calculator approximation, because this doesn't remind me of any of the special angles that we know. Okay, so how do we get this number? Well, this is important. Our answer should be in radians, so make sure your calculator is in radian mode. Where's the inverse cosine button? Usually it's the second button on the cosine key. And if you can't find it, be sure to look in your calculator instruction manual. Okay. Type in inverse cosine of 4/5 and then look at the answer on the screen. Round it off to 4 decimal places as needed, and that's your answer. And I've given you a couple of other ones to try. Make sure that you practice, that you learn how to use your calculator, and that you can get these rounded answers.